also people can maybe anticipate. Oh yeah, okay.
Yeah, that's fine. Okay, so the first question was from Xinliang Shi. I would like to ask, did you do some tensile tests of the SLM 7075 aluminum parts with zirconium H2 addition? What about the mechanical properties? It was a 1015, so it was for our first speaker.
Yeah, I think it was for me, Manas, for Teresa. And
yes, Teresa.
I answered in the chat, but I can answer. Actually, Xinlian, we didn't do a study of the mechanical behavior because we were observing these new features of the microstructure, and then we focused our study on the analysis, and the characterization of the microstructure. But it is true. And so we didn't optimize, let's say, the amount or the volume fraction of particles for structural performance and so on. But it is true that with the amounts that we added, we could eliminate the cracks, but not the porosity. So we still had some porosity levels. So even though we didn't end up testing these materials, but I think the mechanical behavior of those particular samples was not optimized. So it was not going to be very good.
Okay, thanks, Teresa. The next question was from Miriam. Miriam, if you want to ask it. Miriam?
When?
Okay, yeah.
Yes. So, yeah, the question was, did you try to reconstruct those phases, because we have the orientation relationship, so it's possible like to go back to the prior QC to determine more quantitatively the fractions in the before solidification. Now, there are existing tools that permit to do that, and I wonder if you tried.
Yes, we didn't do it. I think it's something that is possible to do. This type of studies would be limited by grain growth. No, that's why I was asking Eric if in these very, very fine microstructures that he produces, if we had observed the grain boundaries, because I think these reconstruction studies would be, it would be great to do them in microstructures that still have, where the grains are still very fine. Mm-hmm. I think there you will have the fingerprint, no, of the nucleation stage would be more evident. But I definitely think that these studies could be done, and they would be very interesting.
Thank you.
Yeah, the next question was from Steve. Good day, Steve. Steve? Okay, so the question was for Maurizio. What is the aging temperature and time used in slide 21 of your presentation? Is the temperature similar to the temperature used to preheat the powder at 160 degrees? If not, what information can be extracted from this comparison?
Yes, it was exactly the same temperature, 160 degrees C. We choose the same temperature for the aging so that we can make a comparison between the artificial aging you can do in a furnace, in a lab, or the, let's say, in situ aging that you can produce during the printing itself. Yeah.
Okay.
But the main point was that you cannot control the time during the printing, because you can set exactly the time of printing and therefore the time of aging. While in the furnace, you can turn on the furnace when at the optimal time. That was a main point, a key point in my opinion.
Okay. And the next question was again from Miriam. So,
yeah. This question for you. Yeah. So the ABSD maps that you showed for that example after the zirconium-based addition. I mean, are we sure that this is because what you see is the 2D section of the microstructure? Can it be like, for example, columnar in the other direction?
Yes, now I see your point. Actually, there were vertical sections, so section parallel to the building direction, to the Z direction, the usual one.
Okay.
And so, in principle, it is roughly speaking along the columnar direction grain growth. yeah, there might be some misalignment. You are right, but yeah, I guess in some cases we have very equiax grain. You could see very clearly equiax grain. Some other cases you could see some other still columnar grain. So I guess there's a question about the mixture of the zirconium was, I think, yeah, zirconium or non-homogeneous, let's say, solidification condition. We could focus more on that. I'm not sure, so it's an open point still.
Okay, thank you.
Okay, so the next question was also for Maurizio from Gishwan Lee. Is he here? No. Okay, so he congratulated on the presentation, and then I don't know if it's a he or she, but they, for the aluminum plus titanium plus B4C approach, it seems the B4C and unmolten titanium particles are quite large. Do you have any idea how those particles would influence the ductility, or whether cracks would preferentially initiate from them during deformation?
Starting from the last point, did not have any evidence of cracks that could start from those particles. And about their effect, well, it is claimed from the producer, by the producer, that it could become a composite material. I mean, you could, by adding even more particles, you could have a kind of composite material made up by a matrix of aluminum and some rigid, very stiff particle inside it. I don't believe too much on that opportunity, and but question of opinion, I think. For sure, for the case we investigated, we had very few particles, and for that amount of particle, I would not expect to have a specific strengthening, significant strengthening.
Okay. Well, another question for you from Marvin. Two questions. The 2000 series are known to gain significant strength after heat treatment due to precipitate formation. Have you checked the existence of these S phases in the modified 2000 alloys, more copper or titanium and B modified alloy after heat treatment? And can you observe a strength enhancing effect?
I wrote on the chat, it was a really good question. I feel a little bit embarrassed because I signed some non-disclosure agreement for a company on this, about this topic here. So I cannot tell you so much things. He got the point, I think.
Okay.
And that's one of the main points. And also relates, and this question also relates to my comment I made, I think, in the very end of my talk, when I claimed that we shall design alloy not starting from old alloy, but we shall start from the very beginning. So there are lots of elements that are not useful anymore. That's the point. And maybe some other can be more significantly or more effectively exploited. Yes, in case of the aging, we lose some strengthening from the aging because some elements they go around and they precipitate not in the very effective form. And but maybe there are some other elements that could be used for improving the strengthening effect after the aging. Sorry if I've been a little bit cryptic, but okay.
No, that's fine. So I suppose, can you answer the second question on the size of the formed titanium carbon dispersoids in the aluminum titanium B4C alloys?
They are sub-micrometric, very small. Yeah.
Okay.
Thank you very much.
Okay.
Thank you.
Sorry if I.
Oh, sorry, you were here, Marvin. I'm sorry, I didn't see that.
Yes, no problem. Yeah, but thanks a lot for the answer. It was very interesting presentation. Thanks.
So the next question was from Philip to Aude.
Yeah, he's more suggesting a paper I should have a look at, and indeed we already exchanged by email during lunchtime about this paper. So it's indeed a very interesting paper that they wrote, and this actually there is a relation to the next question that is for me. So I'm just going to jump from it. But there was a question about whether friction star processing compensated the fact that during heaping we don't really close these porosities, and so they reopen. And well, what I can certainly say is during friction star processing, and so that's a question of Abdullah. During friction star processing, well, we know that we're welding. It's a welding process. So hopefully we can weld. That's something, and the fact that hot isostatic pressing doesn't allow for the same strength level to manage having improvements in fatigue life, and so delay initiation of fatigue cracks. Well, I strongly believe that friction star processing does well allow to close them, and HIP doesn't, and that could explain it. So that answers two questions in one.
Okay, and then the last question was from Milad Hamidi. Yeah. If Milad is here.
And that one.
Can you repeat the question, Aude? Yeah, just to.
Yeah. It's about residual stresses.
Oh, right. Sorry. I was asking if you had the chance to somehow measure the residual stresses for these categories that were presented. And also one point that was not clear was what was the stress ratio that you used in the fatigue experiments, and whether or not you did any kind of correction to see these residual stresses would somehow change the stress ratio for the samples that are with the compressive stresses, basically, because when they are shown in the same Vogler curve, and this is not clarified, I mean, these improvements are not very well, they could not be very well justified.
Well, thank you very much. This is a very relevant question. And so I have first for the stress ratio, that indeed wasn't mentioned. It was a 0.1, and I should have presented that. And then I'd like to share my screen quickly because I can answer with a graph of the second question. So I'm going to do that quickly, if you allow me. This is a paper that is a 2020 paper in additive manufacturing, where we measured the residual stresses into these materials, and here we show the residual stress profile for the aluminium with 35 degrees platform, and we also compared with the 200 degrees platform. As you can see, the residual stresses levels is not so high. We had to fight with the reviewer to allow keeping this one in because I thought that was quite interesting. This is after friction star processing. And as you can see, the residual stress level is much higher. So your argument is totally valid. Will that influence the fatigue life? We don't know yet because we haven't actually got a chance to test structures. This is something that we'll do for making larger fatigue tests, and then hopefully keep some of the residual stresses. These residual stress levels are quite common in friction star processing. So indeed that would be of interest to look at.
Thank you, Aude, for the answer.
You're welcome.
Yeah, so that was the end of the questions from the morning session.
Yeah, and I had some suggestion for a discussion for this morning's, if I may. I had a feeling seeing the three presentations we had this morning, and mostly the two first ones that excluding mine. So the trends in the aluminum alloys additive manufacturing is mostly related to high strength aluminum alloys, and that's no surprises. as the aerospace industry is taking over, as performance is sought for, and so on. So it looks like this high strength solutions now with TI and all other inoculants and zirconium hydrides are working quite nicely. And I think the trend now should be maybe the design of alloys that were now adapted for additive manufacturing. We took these alloys, and I think Maurizio mentioned that. And so I thought that if someone wants to, comment on this, on what should be the future trends in these aluminum alloys, I'd be glad to listen to their thoughts and maybe share some of ours. Anybody? I think, yeah, Maurizio, yeah.
Yes, if you want, I can add a few more comments. Now, I mean, the main point is that the standard alloys that have been developed many years ago for road application, for plastic deformation, forging, whatever it is, they contain lots of elements that are not needed anymore, right? So secondary elements that can control recrystallization, that can keep under control the grain growth, they are not needed anymore, right? And with the same holds for casting alloys. And with additive manufacturing, we have some other requirements. And also we could rely, in my opinion, on slightly different strengthening mechanisms. I mean, for instance, we already have a very fine structure, okay? Provided we can keep the equiaxis grain, we already have very small grain. So grain strengthening, grain numbers, whole patch strengthening is one of the main ones which we could preserve and try to build everything around that, for instance, right? And also, we learned that we have some high temperature dispersion precipitates, such as the trialuminide, titanium, scandium, whatever. They can be more successfully exploited, playing two roles, refining and strengthening. Perhaps new alloy, they should head this direction rather than having lots of elements that are to produce very complex precipitates at very low temperature. And such temperature we cannot control anymore. We cannot, we cannot keep them under control because there are so many turbo cycles during the processing. So the main point, in my opinion, is that we should clear the table and start from very simple alloys, adding few elements that are really needed, and get rid of the rest.
Yeah, and I was also thinking of the ideas that were shared this afternoon, like you have these ODS alloys, and these are solutions that are not so much exploited in aluminum alloys, but as we're talking about powder, why not start with original ideas and just forget about the past of aluminum alloys where they were just putting things, bits of this and bits of that. And here we have a whole new playground for making original changes.
On the other hand, I mean, I totally agree with everything that has been said, but on the other hand, so we also discussed this along similar lines over the last years with one of my PhD students developing aluminum alloys. The problem is if you go this, let's say, bottom-up approach, like we have a complete new playing field. Now let's go ahead and build a new aluminum alloy only for LPBF. If you do that, I mean, after 3 years of a PhD, maybe you have something, if you're lucky, that is processable and that has a decent strength. And then the first reviewer comes, yeah, but what about fatigue? And then the second reviewer comes and says, yeah, but what about corrosion? And then they start talking about stress corrosion cracking or whatever. And so this is the point where you start thinking, maybe we should have taken an existing alloy and just made it processable. And then we already, build on top of what has been shown to be a nice balance of properties.
No, certainly, I agree with you, and we're doing exactly the same. But it's just that, I'm trying to open the debate here on whether we could maybe think differently. But I agree with you. This is a long-term process, and we should accept that maybe this is not going to be fantastically working. I see Christian turn on the microphone.
If I might chime in. So what I see, and this is also the feedback from industry partners, is that they like going with the alloys they know. Really that should be a whatsoever 2000 or 6000 series. And they really like that because everything in-house has been adjusted also to that. However, what we see is that the specs, they're usually rather broad, and we have observed that this still leaves some playground that you can adjust the amount of certain elements without really changing the specs too much. So it is actually really an alloy of that certain type, but you made it more processable. I'm not speaking only about adding zirconium or so to it. There are also possibilities to change the amount of certain other alloying elements, and that is accepted also on the industry side, at least more accepted than really going for the bottom-up approach and come up with a completely new alloy. What they don't know, they will not buy it, and it would take too long to introduce it.
Yeah, I had the same kind of discussions, and also something interesting if you're working with a 7075, for example, which has a tight range in magnesium and zirconium and zinc. Sorry, you might actually evaporate some of it in the process, and so you get out of these ranges, and that is an issue actually also. So so one of the reasons why I think we should think maybe about new ways of processing also.
I was quite impressed when I was at TMS in 2020. So, back when we could still travel. And I heard a bunch of talks about the development that is ongoing in the US about, I think it was aluminium cerium eutectic alloys. But that was really, I don't know the background of that, but it really sounded like it is a concentrated effort of many different institutes all working together on the same type of alloy, pushing it forward in various different areas. And I think that makes a lot of sense.
Yeah. Let's say there's a general trend going for eutectic alloys other than aluminium silicon, which aluminium cerium and then also these variants, these ternary alloys are. However, I have reviewed a couple of papers also from them, probably you too. What I see is that they are still very, very brittle. So strength is good, but ductility is very low.
Try friction stir processing, that will improve it.
And I think also a thing when you talk to industries is that availability of raw material, recyclability and stable price is also important. So whenever you start to add exotic things, they are always, that's the reason why they are looking for alternatives for scandium, because calmalloy is, it has problems maybe with recrystallization, but besides that, scandium, metallurgically, it's a fantastic element. The way it is similar to the crystal lattice of aluminium, the way it has different solubility in liquid and solid, the way it acts as a stable precipitate is fantastic, but it's rare and it's expensive.
Yeah, the price is fluctuating up and down, and so you can rely on it. No, actually, I fully agree with what has been said. I was simply mentioning a kind of scientific approach, but we all know that companies they use specifications, and they will never leave apart specification and jumping into something new. So they will never leave something that is well established for something that is new. So it will be a long process. We all are, I think, we all are publishing papers on modification of alloy, and while in the lab we are working on something new, maybe in the next years.
Well, thank you very much. I enjoy very much this conversation. This is exactly the type of things that we should have in presential, of course, but it was great to have it still online. Yeah, so I don't know if anyone else wants to start a similar topic on something else and copper or the alloys or else.
Yeah, I would really be interested in hearing your opinions on the ODS alloys, yeah? Because you know, the ODS alloys economically are not viable in their, at least this is what I've been told, in their original processing route. And if we could via an additive manufacturing route make them viable and you know, scientifically interesting and economically possible, that would be really good. But I don't actually, when I talk to people, not many people are interested in ODS alloys in industry, for example. I don't know if you have different opinions or experiences.
Well, I think in the nuclear sector, there is for sure interest in ODS alloys.
Yes, but
Yeah.
they like to really have sub 10 nanometer sized oxides. And we have tried that, and that is a problem. So we always see a certain growth, and they do not want it for strengthening, but actually for taking up also the helium also that is forming in these reactions. And for that, I think they become just too large. We have tried, I showed that on my last slide, we have tried fabricating a couple of alloys. So the solid solution strengthened alloys, they work quite well. However, there we have not really seen a significant strengthening effect. And on the oxidation side, it can go in both directions. In some alloys, we see a strong increase. In other alloys, I haven't also put it there, that was the MAR M230. We saw the opposite effect, which we say it's overdoping, because always some yttrium or so goes into solution and can have an influence on something that you do not expect. I don't know. I mean, we've been now actively working on that, and I think there is no general answer to it. It really depends on the alloy and the properties that you want to improve. It's certainly a way to give them more complex shapes than what was possible before with ODS alloys, which is really bars or sheets or really rather coarse geometries.
Maybe what's also one of the reasons why these were made by powder metallurgy, but more classical. I mean, powder metallurgy not involving melting, because maybe that avoided this growth, right?
Sure. I mean, before with welding, so these slagging issues, they have been known. So if you really have a very high energy input, there are these reactions, and you have slags coming up. I mean, that was our approach, not only ours, but also of other groups, that we thought the solidification is fast enough that we can mitigate that. We could show it works to a certain extent, but ... So there are still a couple of things that we have to look into.
Christian, you showed that you had some precipitation of intermetallics at the grain boundaries. How big a problem or benefit is it to have those, and what else do you see besides intermetallics? Could you, for instance, did you see any non-oxide precipitates forming?
We saw them only in the as-processed state, and they disappeared completely after the heat treatment. So they are not stable. What we have seen in other alloys is that some intermetallics can form, but very often they are metastable and they dissolve upon also a heat treatment. Concerning their potential strengthening effect, I mean, in the heat treated state, it's just not there. I'm a bit more concerned that they form some low melting eutectics or so that make processing more challenging. I don't know whether there is really a significant effect on strength or other properties coming from those.
Okay, because in this 316L steel that we processed with DED approach, we saw that 70% of the precipitates that we tested with TEM were actually mixed oxides, mixed precipitates with either one oxide and one non-oxide, or just purely two non-oxides inside. And so just the sheer density of your oxides, if it increases, it can affect the strength in that sense. And if you heat treat that and it does not go away, then what really, like the problem that you are facing is to understand whether it's good to have slags or it's better to have dispersoids, and how do those two affect the sample of your material. But the problems we are facing is, besides those things, we also have non-oxides present, as I will show tomorrow. So, yeah.
I think this is a perfect transition to present tomorrow's program, if we are done with the discussion. So you have it? Yeah, okay, perfect. Tomorrow will be two modeling work by Charkaluk and Damien Touré from France and Spain. And then we'll have a combined experiment and modeling work by Manas. And I understand he's going to also talk about in situ XRD, SEM results, and so on. So that there will be some spaces for experimental people, and there will be some modeling work tomorrow. And we'll still have some discussion time. So if you want to think about general questions on which you want to just jump in and start the discussion, you're most welcome to do so, because I think this is a really nice opportunity we have here. Unfortunately, it's difficult to have this in a virtual way, but let's try it. And I think this session now just proved that it's possible to have a bit of a discussion. And of course, feel free to contact people after.
El otro día estaba escuchando yo la radio y me dice, mamá, quítame esto, que esto no es música. Ponme...
Yeah. Okay. That was Teresa speaking Spanish. Okay, so well, I'll see you all tomorrow, 9:30. Thank you all for the speakers of today. It was really a great session. Thank you for the good discussion, and looking forward to see you tomorrow. Have a nice evening.
Thank you.
Thank you. See you tomorrow.
Nice evening.
Thank you.
Bye-bye. See you.
Bye.
Thank you. Bye-bye.
Bye.